Hello, this is the continuation of question 3 from test 2 of 2020. And remember in part A, we had this reaction here that we're looking at, and using Hess's law, we found the enthalpy for this reaction. And in this question here, part B, it wants to know delta U. So your equation for delta H relationship to delta U is this one here. We have delta U plus delta PV. So rearranging for delta U, we end up with delta U equals delta H minus delta PV. So we have delta H already from part A, but it's this part here that we need to look at. And remember, this is not an expansion and compression of ideal gases. So in order to find these answers here, go back to your ideal gas. This is an equation. Delta PV is going to be equal to delta of nRT. In this case here, our temperature is constant. You're doing a reaction. So it's really the moles that are changing. And we don't care about moles of solid or liquid because they don't affect this PV function in any way. We don't really have expansion or compression of solids and liquids to that extent that it's going to affect delta U or delta H. So, or delta U in this case here. Really, you're just looking at the change in the moles of gas from the reaction. Okay. Now, if we get that, it's the products minus reactants. We want to find delta N. This is the sum of all the moles in the products minus the sum of the moles in the reactants. And remember, only gaseous ones. So this here equals, you have no gas molecules in the products, 0 minus in the reactants, 3. So we have minus 3 moles for that value. So putting it into your equation for delta U, you have delta H minus delta N gas RT. So this will be your minus 3 value right there. This is our gas constant, 8.314, and our temperature at 298. Keep in mind, this is giving you a value in joules, and what you have from the first part is in kilojoules. So make sure you do some form of conversion, either here or there, to make sure you're working with the same units in each case. Now, if you use the correct answer from part A, delta U equals minus 276 kilojoules. Now, let's say you had the wrong answer for part A. As long as that answer for delta U equals whatever you had for delta H, as long as you've done this all properly, plus 7.4 kilojoules. Okay, so that's part B. Now, if we look at part C instead, I'm just going to erase most of this right here. In this case here, it wants to know the amount of heat needed or released during the preparation of 4 liters. So in this case here, heat, because this is done at constant pressure, the heat at constant pressure is delta H. Okay? So we know delta H for the reaction as written, but we don't know it for 4 liters of CCl4. So you're given a volume of 4 liters. We have the density of carbon tetrachloride of 1.59 grams per milliliter. So we can find the mass, in this case here, and make sure you do your conversions. This is 4,000 milliliters, so you should have a mass of 6,360 grams of carbon tet. You're also going to have to find the molecular weight of carbon tetrachloride. And once you have that, you can find your moles of CCl4. So you should end up with 41.4 moles of CCl4. So this should have been pretty straightforward. You don't even need your answer from part A at this point here. Now you do. So in this case here, if you remember, so from part A, or whatever number you did get, you take that into consideration. So delta H for the reaction was minus 283.5. That's kilojoules. And if you look at the way it's written, it's per mole of CCl4. Per mole of CCl4. And we have 41.4 moles of CCl4. So we can find delta H for the 4 liters minus 11,700 kilojoules. That's how much the heat is released during this process. And again, here, as long as you had this correct, whatever, and the value that you'd happen to have for A, you shouldn't be penalized as long as everything else is correct there. Now let's go to D, get it all done on the 1. So in this case here, now you're using your answer from part A again, and sum of the values from the list. And we want to find, I'm just going to erase this totally. You want to find delta H naught of formation for CS2. Now, if you remember delta HF of formation, this is forming 1 mole of the product from its elements in their standard states. So the elements, we have carbon, that's carbon solid or graphite, and then sulfur, the way sulfur shows up, sulfur also solid. And so to balance this out, we would need 2 of those in order to make the CS2. So really it's the delta H of this reaction. So there's 2 ways to go about getting this answer. One is to use a pile of the values or pile of those equations from part A, cancel out what you don't need to find using Hess's law, really. And the other way, which really is also Hess's law, but instead you're using an equation for this. Now, what you can realize is that first equation that we did look at, so CS2, including CS2, so the one that you had to find delta H for, okay, because it does say using your answer from part A. Now, in this case here, you have delta H for that reaction, right? Remember how you get delta H of a reaction? You have delta HF is the sum delta H naught F of all the products minus the sum delta H naught F of the reactants. So in this case here, it would be delta H naught F of CCl4 plus delta H naught F of S2Cl2. So those are our 2 products that we have in there. And then you have minus delta H naught F of CS2 and 3 times delta H naught F of Cl2. Okay. So if you remember the heats of formation, you're making the compound, 1 mole of the compound from its standards, from its elements in their standard state. So for chlorine, this is 0. Making itself from itself doesn't make any sense. So that value there is 0. This is the one you're trying to find. You know delta H of reaction. And if you go and look at your list, these guys might happen to show up. So formation of CCl4, that's the one at the bottom. That is, this value that you have here is the enthalpy of formation because you're starting from the elements in their standard states, carbon and chlorine. Now the other one is the S2Cl2. Equation number 2 has that written backwards. Yep. So you'd be forming the S2Cl2 from its elements in their standard states, and that's the value right there. You can find this one and this one from the table, that one you've calculated. So in the end, the answer that you should find is 89.9 kilojoules. Okay, there you go.